Hello students and welcome back to this new session. Here I'll be discussing the topic of solution of linear differential equations using Laplace transforms. I hope you all are familiar with the name linear differential equations, or you all are familiar with the topic linear differential equations, which we have learnt in our previous semester. Okay, the linear differential equations with constant coefficients, generally I have written it on your screen. It is a naught y double dash plus a1 y dash plus a2 y is equal to phi of t. Here a naught, a1, a2, they are all constants, and you see they are all, it's a linear differential equation. Degree of each term is 1 here, and it's a second order linear differential equation with constant coefficients. Okay, so phi of t is any function of t. It can be any function of t, exponential, trigonometric, or any polynomial in t. Okay, so you'll have learned the solution of linear differential equations by direct method in our previous semester, but now we will discuss the same topic, linear differential equations. We'll solve the linear differential equations using Laplace transforms. So this is one of the important applications of Laplace transform, solving a linear differential equations with constant coefficients. Okay, let's see how to solve this using Laplace transform. Okay, so before starting with the actual topic here, I just want you to give a small idea behind that big formula which I'll directly be giving you. Proof is not there for you, but just pay attention, all of you. Just for example, first of all, the method of solving a linear differential equation using Laplace transform is very simple. That is what, you take the given linear differential equation and apply Laplace transform throughout. Okay, so if you apply Laplace transform throughout, a naught you will keep aside, Laplace transform of y double dash it will be, plus a1 aside, Laplace transform of y dash it will be, plus if I just write it, it will be something like this. If I apply Laplace transform to this equation, for instance, it will be a naught Laplace transform of y double dash, plus a1 Laplace transform of y dash, plus a2 Laplace transform of y is equal to the Laplace transform of the right hand side as well. It will be something like this. Okay, Laplace transform of the right hand side. So I know the Laplace transform of y, it becomes y of t, y bar of s. Suppose, okay, I can write it, but what should I do with the Laplace transform of y dash and y double dash? For that I should do something. I should know what exactly it takes the form. So for that, let us understand what is Laplace transform of y dash, then we will continue with y double dash also, to y double dash also, and then we'll so on, we'll do it. Okay, and we'll generalize and take the formula. Okay, so now see here, let us consider the basic definition for the Laplace transform. We know that the Laplace transform for any function f of t is defined to be integration from 0 to infinity e to the power minus st f of t dt. So we know this. Now I want the Laplace transform of y dash of t, suppose. Okay, y is a function of t here. Okay, and y double dash, y dash, you all know they are all the derivatives of y with respect to t. So we are going to consider Laplace transform of y dash of t, integration 0 to infinity. In place of f of t, I just need to write y dash of t, e to the power minus st y dash of t dt it will be. Is it not? Now to solve this integral, I will use integration by parts. Okay, now I hope you all remember what is integration by parts. Integration of u into v, where u and v are the functions of same variable, say x. Now integration of u into v, we know that it is u under integral sign v minus under integral sign u dash integration of v, and so on. Okay, I'm going to use this formula over here. Say suppose this is my u, this is my v. Okay, why I am doing this as u, this as v? Because I know the integration of v with respect to t. Now here it is y dash there. So if I integrate y dash with respect to t, it will get y of t for me. So I know the integration of v as well. So this as v, if I take, I know its integration very well. So my work goes very simple. So for that I am choosing this to be v. So now let us keep u as it is, e to the power minus st as it is. Integration of v, it is nothing but y of t, as I told you just now in my explanation. Integration from 0 to infinity, this is going to be my first term, right? Minus under integral sign from 0 to infinity again. Now u dash you are going to write. U dash means what? Derivative of u, that is e to the power minus st with respect to t you are doing. So it will be minus s into e to the power minus st. Derivative of e to the power minus st with respect to t is minus s into e to the power minus st into integration of v, whatever you had written over here, that same you are going to write, that is y of t comes over here into dt. Is it not? Now this is equal to, now see, if you put t as infinity, it becomes 0. Because e to power minus infinity becomes 0. The upper limit for the first bracket is 0 minus the lower limit. When you put t as 0 over here, e to power 0 becomes 1. You will have y of 0 over here. Means the solution for this complete bracket here with upper and lower limits, you are ending with y of 0 minus. I'll take that minus s outside. Okay, so it becomes minus of minus plus s. Integration from 0 to infinity e to power minus st into y of t. Now what is this? What is this? You just refer this standard formula of Laplace transform of f of t. It is integration from 0 to infinity e to power minus st f of t dt. In place of that f of t, you have got y of t. Only that is the difference, rest everything is same. So means what? You have here y of 0 minus y of 0 plus s into, I can write this as y bar of s. That is the Laplace transform of y of t. Means what? The Laplace transform of y dash of t can be written as s into y bar of s minus y of 0. I hope it is clear to you. Yes, this is one, say suppose this is equation 1 for you. Now I will continue it for the Laplace transform of y double dash of t. Now let us consider y double dash of t, and I will do the same work what I have done for y dash of t. Okay, just follow it. So integration from 0 to infinity e to power minus st you will have, y double dash of t you will have, dt you will have. I'll use the same formula of integration by parts and do the same stuff whatever I have done before. So now this will be equal to what? This will be my u, this will be my v. I know it's integration of y double dash, it will be simply y dash. So the bracket will have e to power minus st into integration of y double dash of t, it will be y dash of t. Is it not? Integration of y double dash of t with respect to t will be y dash of t with limits from 0 to infinity minus under integral sign from 0 to infinity e to the power minus st. Sorry, 1 minute. We are going to write the derivative of u now. So it becomes minus s into e to power minus st into the same thing whatever you had written here, y dash of t dt. Okay. Now if you solve for the upper limit, e to power minus infinity will be 0. So the upper limit is 0 for this bracket minus the lower limit becomes what? Y dash of 0. Because e to power 0 is 1 and the lower limit if you put t as 0 over here, it will be e to the power y dash of 0 and e to power 0 is 1. Okay, so complete this bracket minus, you can take that minus sign outside, plus s it will become integration from 0 to infinity e to power minus st y dash of t dt. Now what is this? 1 minute. Okay, now tell me what is this integral? You just go back to your previous this. It is nothing but this itself. Yes or no? It is Laplace transform of y dash of t, and for Laplace transform of y dash of t we have derived it as equation 1. I will simply substitute the value of y dash of t over here, that is Laplace transform of y dash of t over here. It is here, see, I will substitute it here. So it will be what? Minus y dash of t plus s into, we are going to write it s into y bar of s minus y of 0. Or if you further simplify this, it will be s square y bar of s minus s into y of 0 minus y dash of 0. This is my second equation. Means what? If you are having any derivative, suppose for first derivative you have got 1s y bar of s and y of 0. If you are taking second derivative, Laplace transform of second derivative, you will have s square y bar of s minus s into y bar of y of 0 minus y dash of 0, and it so on, it continues. So if I generalize this entire formula, I hope this is clear to you. You can continue it for the third one also. Similarly, I'll just write in general here. First I will write it for the third one, then we'll write the general value, okay, general thing. So now see here, if I consider the Laplace transform of y triple dash of t, we want it to be s cube y double y bar of s minus s square into y of 0 minus s into y dash of 0 minus y double dash of 0. It will be like this. S cube y bar of s minus s square y of 0 minus s into y dash of 0, yes, minus y double dash of 0. Similarly, fourth derivative, fifth derivative, and so on. Finally, if I continue it, it continues, and I can write y, suppose there is nth derivative, Laplace transform of nth derivative of y with respect to t can be taken as s to the power n y bar of s minus s minus 1 into y of 0 minus s minus 2 into y dash of 0. Yes or no? I'll generalize it. I'm just generalizing, nothing else. Okay? Minus s to the power n minus 3 y double dash of 0 minus so on minus at the end you will have y to the power, it was third derivative here, so you ended with the second derivative at the end of 0. So if it is nth here, it will be n minus 1 of 0, n minus 1th derivative at 0, it will be like this. So this is going to be our important formula for solving the problems using Laplace transforms. Okay, so you need to remember this important formula. Okay, it's very simple to remember also. I'll just give you a hint to remember. No matter what is the derivative of y you are considering, that the n should appear as here and y bar of s minus s, whatever you had written, one number less to this, s to the power one number less to the previous one, but here it will be y of 0, always the next term will be y of 0 minus again one power less than the previous of for s into y dash. Earlier we had only written y of 0, now it becomes y dash. Third, again y double dash it will be. Again of n minus 3 y triple dash it will be, n minus 3 y double dash. Similarly, it continues. At the end, look at the, you just compare with the previous term. You had got a third, for the third derivative Laplace transform, you ended with the second this, and there is no s along with it. Okay, the previous term to this also you can write. 1 minute, I'll just show you. Minus so on, minus s into y to the power n minus 2 of 0 you will get. Okay, look at this. It was 3, you got first y dash of 0. Okay, so therefore minus 2 you can write for any n. Okay, so minus and so on. So this is going to be your generalized formula to work for the integration by the Laplace transform, using Laplace transform, finding the solution for linear differential equation using Laplace transform. Okay, let me continue it. So this is just the explanation how to use the formula. For those who have not understood, please do ask me in my WhatsApp group, you will understand. I'll just give you certain hints there, but still you just refer this, it will be easy for you to remember it. Okay, in my next session I will continue with the problems. Okay.